Okay, welcome. You hear me okay? Hello? Okay. Good morning. I want to welcome you. Cosmic Frontiers, the planets. This is the second time we've done Cosmic Frontiers. Last year the theme was Stephen Hawking and the universe. This year the theme is the planets. I want to acknowledge all the speakers for giving up their valuable time to be here. I want to acknowledge the planning committee for figuring out the program. And I think we should just go ahead here and get moving with the agenda. I want to remind you that you're on a planet at the moment. Almost nobody that you know has ever left this planet. The official boundary, or the accepted boundary, is here, the Kármán line. Very few people have gone above that line. There's one person in this room who has done that I'm aware of. Maybe somebody else I'm not aware of. So we're going to have sessions today and tomorrow about planets in our solar system. That'll be today. We'll talk about exoplanets, and then we'll talk about tools to study planets. Since many of us will never experience visiting another planet, that's one way that we can think about the other planets that exist, is through tools to analyze them. So there'll be a number of talks about that. And it's my pleasure to stop talking now and turn it over to the session chair and the chair of the steering committee, Dr. Lisa Danielson.
Oh, there it is. See this? There we Oh, thank you. Oh, so you just tilt. Oh, that's genius. Thank you. I was about to do my usual tippy toe thing that I do after I go, oh, right. I'm a Hobbitses. I'm so excited to welcome everyone to our opening of Cosmic Frontiers again. Last year was fantastic. This year, I'm really looking forward to an overview of the different ways, even though we haven't maybe physically left this planet, we can leave this planet and we can investigate planets inside and out. This is very important. People don't think about this, but 99+% of every single planet is on the inside. So we are going to hear about that in a later talk. But we also typically investigate other planets remotely via our astrophysical observations, sometimes robotically, etc. And so I'm excited to get different overviews, different perspectives, learn about how all of us experience planets and planetary exploration in different ways. So with that, I'm going to turn it over to our first speaker. Welcome, who I am hoping is going to talk a lot about all the different planets in our solar system, including my favorite. It's right here, sponsorship. Bryan Butler is going to talked with us. And for those of you that are in, let me just do a quick housekeeping. For those of you who are in the morning session, again, please pay attention to the clock to keep us on time. If you get close, as you approach the 1 minute mark, I'm going to stand up, kind of sideways crab walk affectionately to you. And, you don't want the gentle hand that says, please, let's move on. And we do want to save time for Q&A, and we will be around with the microphones. Colin and I will each take a side, and please use those because we are doing a broadcast, right? And that's the only way the good people listening in remotely are going to be able to join us. Okay, so with that, I'm so excited, Bryan. Come on up. Welcome, Bryan.
I'm a little tired.
Oh, you sure you don't want to live my life?
Okay, hi. My name's Bryan Butler. I'm a staff scientist at the National Radio Astronomy Observatory. I live in Albuquerque. I worked for a long time at our office in Socorro, and for the last 5 years, we opened an office in Albuquerque, and so I've been working there and from home, of course, during COVID. I'm going to tell you about observations of solar system objects at what would be considered long wavelengths to most people, millimeter and centimeter wavelengths. But first, since, you know, there are a lot of students in the crowd, I thought I would give you a little, you know, what was my path? How did I end up here where I am now? So this is fourth grade me, wearing an appropriately long collared shirt in the 1970s. I grew up in the 1960s and 70s, and so there was a lot of sort of new science fiction on television, in the movies, books, and I consumed it voraciously in some cases. I went to the premiere of Star Wars. Of course, Apollo was going very strong then. I watched the first moon landing. So I was really motivated by wanting to know about space, but I really didn't know what I wanted to do for sure. So when I graduated from high school, I went to college at Utah State, and my father convinced me that I should have a more practical sort of engineering background, and computer science was still relatively new at that time. And so I have a double major, but two actual diplomas, one in electrical engineering and one in computer science. And part of that was because I spent a semester in Alaska working on software. I had written some data collection software for a sounding rocket, which was launched into the Aurora. Utah State has a very strong upper atmosphere program, and I took all of the undergraduate and graduate courses. It was all Earth atmosphere, of course, but I still didn't really know what I wanted to do. So I applied to a lot of universities for graduate school. Well, I applied for a lot of jobs. I really didn't like any of the ones that I could have taken. And I went and visited, and when I went to Caltech, I was like, the planetary science department there was a perfect match for me. So I went to Caltech for graduate school, PhD in planetary science. And that's 23 years of school, and 24 if you count kindergarten, I guess. But what came out of it was a career that I'm extremely happy with. You know, I wouldn't change the trajectory my career went on. But one of the lessons is that, you know, you don't really have to know what you want to do all the time. You may be very focused on, I want to do this or this, but keep your options open, follow your path, and where you end up, make sure you're happy. And if you're not, do something else. So I work mostly with the Very Large Array. Some of you may have been there. Down, if you go to Socorro, go west on Highway 60, past Magdalena, and I'll have a map in a bit, about 30 miles, it's 50 miles from Socorro. I've spent a lot of time developing new telescopes and upgrades to telescopes. I took a diversion and spent about 20 years in management. I've been out of that for about 5 years just before pandemic, so I'm much happier now. Okay, so to the real meat of the talk. I'm going to assert that you can find unique information about solar system bodies by looking at them with long wavelengths. And the reason is that long wavelengths probe to unique depths, either in subsurfaces of solid bodies or in deep atmospheres. So I'm not going to defend that in any way because I don't have time. And unfortunately, I don't really have time to go through the theory, and I don't have time to cover every planet. So I'm going to give you a little bit of background and then do two examples, one from VLA and one from ALMA. And I'll describe what those telescopes are. So surface or atmosphere emission, any body that is above 0 degrees temperature emits black body radiation, and that's at all wavelengths. It's peaks in the, well, it depends on the temperature of the body, but typically in the infrared or into the submillimeter. So we can receive that if we have sensitive receivers, telescopes, big telescopes. We can receive that either from surfaces or atmospheres and then make images. These are actually optical images, so I'm cheating. And this is actually an image of Mercury from one of the Mariner missions that passed by. This is Uranus from Voyager. Okay, There are other things that can be done at these long wavelengths. For instance, we transmit from very large transmitters. Unfortunately, Arecibo is no longer available. It fell apart. But we still use Goldstone, which is a 70-meter aperture, and we can transmit up to a body and receive what's reflected off of the surface. There's also emission from excited electrons in magnetospheres. This happens on Earth. I mean, this is the Van Allen belts, essentially. It really only happens at a detectable level on other planets at Jupiter, because its magnetosphere is so strong and it traps a lot of electrons. But I don't have time to talk about all of these things. Okay, theory of emission in one slide. These are the only equations I'm going to show you. But the important thing to know is that by using the observations and models, typically, of the emission, you model the temperature and then you model the emission that's coming out. What you do is you typically have a number of things that you assume are known. They may have been measured. For instance, on the moon, people went there and measured many of these surface properties. Mars, we've sent a bunch of spacecraft there. So you assume some of them are known, and you solve for the other ones, for the unknowns. So, and you could do that either for surfaces or for atmospheres. Okay, so arguably the two most powerful telescopes to do these kinds of observations at centimeter and millimeter wavelengths are the VLA here in New Mexico and what's called ALMA. So VLA is at centimeter wavelengths. It's bigger telescopes. And again, the next few slides will cover this in more detail. ALMA is a bit smaller telescopes, much higher wavelengths, and at a very high site in the Chilean Andes. In fact, these two telescopes they're only used between 5 and 10% of the time to look at solar system objects. They're typically looking at stars, at star formation regions, at forming planetary systems, at extragalactic things, other galaxies, at the cosmic microwave background, all sorts of things. Okay, so the VLA, if you haven't been there, you should go. It's a fantastic place to go. You can visit. It used to be open access. Now, I believe they want you to make an appointment, and it costs a few dollars to get in. But there's a self-guided walking tour. So you go south on the freeway, turn off at Socorro, go west on Highway 60, and you'll hit, after Magdalena, on what's called the Plains of San Agustin, you'll hit the Very Large Array. Okay, so 27 antennas. They're arranged in a Y, like on this figure, 9 on each arm, and they're each 25 meters in diameter, so they're pretty big. They're arranged in 4 configurations. We change configurations every 4 months, and it's kind of like a zoom lens, so you can zoom in on things. And the wider aperture, shorter baselines means that you're more sensitive to different kinds of emissions. So each of the configurations has their own sort of speciality. The wavelength coverage is of the main bands is about 30 centimeters to 6 millimeters. And we have an open skies policy, so we're open to proposals from anybody in the world. We have a time allocation committee, science review panels, and we go through a process of choosing what gets to get observed. And it's about 5,000 hours each year on the sky. It's operated from Socorro and from the site itself. Okay, that's a picture. In its most compact configuration, we call it the D configuration. They're DCBA, very original names. Well, like Very Large Array. Okay, ALMA is located in the high Chilean Andes. It's at about 17,000 feet. I spent a lot of time there in the late 90s, early 2000s when we were commissioning the site. Doing site testing to make sure it was an appropriate site to put a millimeter telescope. There are 66 antennas, 54 of them are 12 meters in diameter, so again, smaller, about half the size of the VLA antennas. And 12 of them are 7 meters in diameter, and there are reasons we want these smaller ones so that we can put them really close together. the wavelength coverage is about 9 millimeters to 0.3 millimeters, so 350 microns. It's kind of into the far infrared, not quite, but it's jointly operated between NRAO, ESO, the European Southern Observatory, and a consortium of East Asian, mostly Asia A, which is a Taiwanese, and NAOJ, which is Japanese. It's operated from a site that's about halfway down it's not really a mountain. I mean, in the high Chilean Andes, there are volcanoes, and then everything else is pretty high up. Okay, and that's a picture. It's a bit of a fake because the background picture there is the optical. The sky is in the optical, but you get beautiful views of the Milky Way from there, of course, because it's right overhead. The center of the Milky Way is at southern declination, and so since Alma is at about -11 latitude, the Milky Way goes right overhead. It's beautiful. Okay, 2 examples I will cover. Jupiter. So it's a big gas ball. It's the largest planet by far in our solar system. It dominates the mass of the planets. Of course, the sun dominates the total mass of the solar system. It's got a lot of weather, interesting weather. The Great Red Spot is one example of this. There are very interesting atmospheric dynamics that Raul, who's another speaker, I don't know if he's going to talk about, but he certainly is an expert in this area. It's got rings. They're called the Gossamer rings. You can't really see them very much. They're not like Saturn's rings, so they're not very prominent, but it does have a ring. Okay, so in thermal emission, Jupiter rotates fairly rapidly, so 10.5 hours, if I remember right. So we didn't have enough sensitivity even with the what's called the pre-upgrade VLA before 2010. We didn't have enough sensitivity to make an image before it rotated quite a bit. So we had to average together a lot of data, so we got these longitudinally averaged images. So this is from a more recent publication, but is essentially what we used to get with the VLA. So you get at different what we call bands, and these are essentially frequencies here, but wavelengths. So this is about 1 centimeter. This is about 10 centimeters. So, and you see into different depths. So the reason to do it at different wavelengths is because you probe deeper at the longer wavelengths. So you're essentially doing a vertical sounding of the atmosphere when you do this. But, we were frustrated because, we couldn't make these very high resolution. It was all just longitudinally smeared. So you couldn't see, for instance, the signature of the Great Red Spot. In the early 2000s, a guy called Bob Salt, who I collaborated with a lot. He's Australian. He's retired now, but brilliant guy. He invented a technique where you could take this, all of this data that you took while it was rotating, and then you do what's called a deprojection technique, and then you make what's effectively a cartographic map of Jupiter in a given system. Cartographic system. And you can see here that you can start, this is with the pre-upgrade VLA, so not quite as sensitive. So you can start to see features here. Oh yeah, you can kind of see my my pointer. But the bright features, that's just north of the equator, and that's a well-known thing from the infrared. Those are so-called 5-micron hotspots, and you could start to see them. And then after the upgrade, we made the VLA about 10 times more sensitive than it was previously, and that started in 2010. And we started observing regularly Jupiter. Imke de Pater is the lead. She's faculty at Berkeley, now retired, but longtime collaborator of mine. And so we did this at various wavelengths. This is one example. So you can see it's much higher sensitivity. You can actually see the signature of the Great Red Spot and the turbulent wake behind it. You can see signatures of larger spots. Sometimes these are called white ovals or brown barges. And you can see very, very clearly the 5-micron hotspot band. So this is pretty spectacular because now you can do weather at depth. So we can probe down to, in the optical, you're looking at 1/10 of a bar. One bar being the pressure of the atmosphere on Earth's surface, roughly, depending on where you are. Here it's a little less because we're high up. Here it's about 800 millibars, but at sea level it's about a bar. So you see above that in the optical. In the infrared you probe deeper, but you still are only probing about to about a bar. And we can probe down to 10 times that depth, and at longer wavelengths even deeper. And that's the point of the Juno mission, is to probe very deeply into the atmosphere of Jupiter. The main point was to derive water abundance. I didn't show you a vertical. There are clouds and different molecules at different depths because they make these clouds as the atmospheric processes cause them to actually, just like on Earth's atmosphere, the water makes clouds when it gets to the right conditions in the atmosphere. That happens on all the giant planets, in fact. So we also did this with ALMA. It's not quite as spectacular in some sense because we can't get quite the right resolution. It's also sensing higher up, so this is actually more akin, it's more comparable to the infrared and optical. Okay, next topic, Pluto. So not a whole lot, some was known, but not a whole lot before the New Horizons spacecraft flew by in summer of 2015. This is an image from that flyby. The heart-shaped thing there, the left-hand side of it is called Sputnik Planitia. These are compositional units. They indicate the different ices, mostly on the surface of Pluto. So it's mostly, we think, it's a bedrock of water ice. And then it's got coatings of nitrogen ice, methane ice, and carbon dioxide ice. And it's got lots of interesting geology that people have been studying since that flyby, since the high-resolution images. It's all ice geology, so you might call it rheology, but it's very interesting stuff. Okay, so for a long time, we've known that there's a weirdness with what's called the brightness temperature, which is related to the physical temperature by a quantity we call the emissivity. But you can think of it as physical temperature mostly. So at longer wavelengths, beyond the infrared at least, there's a big deficit in, and I think I'm going to use the pointer. So this is what we expect, and this is what is measured. And so this is way lower in temperature here. You know, we expect 50 kelvins or so, and what we see is more like 30 to 40 kelvins. So that was a bit of a conundrum. Why was that? In the mid-1990s, it was kind of figured out that is the vapor pressure point of nitrogen. So it's not the the sunlight that's maintaining the temperature. It's actually the vaporization and deposition of nitrogen onto the surface. So it's the latent, what's called the latent heat that's controlling the temperature. And Pluto is much colder than we thought. So, but we couldn't, with these older observations, we could never tell whether this was a Pluto thing or a Charon thing. Remember, Charon is not as big as Pluto. It's about half the size, which means about a quarter of the solid angle. But we couldn't resolve the two at these long wavelengths until sort of the early 2000s. And a colleague of mine and I, Mark Gerwell, used the SMA, what's called the SMA, which is kind of like an early ALMA on Hawaii. It's called the submillimeter array. It's operated by Harvard and the Center for Astrophysics and the Smithsonian Astrophysical Observatory. So we could separate the two, and we could tell that, Charon was essentially the temperature that we expected, but Pluto was the cold one. So this just verified the fact that it was this Pluto. On Pluto, this nitrogen ice is what's moderating things. On Charon, there's probably not any or very little nitrogen ice. It's mostly just water ice. And water ice has very different characteristics than nitrogen ice. It's less volatile, and so it equilibrates with the sunlight. So we did this again with ALMA in 2015, much higher sensitivity. So you can see these are pretty spectacular images, but there's some information about the particulars of it. But the important thing was we verified what we knew before, but with much higher sensitivity. But we couldn't resolve each of the bodies separately. At that time, ALMA was not allowing us to. So ALMA it also goes through these zoom configurations. It has more of them, but they weren't allowing us to use the long baselines at the high frequencies that we needed to actually resolve Pluto and Charon. They started doing that in 2017, so we proposed to observe the system at that time. And here you can see, I mean, even on this scale, you can see with your eye that there's detail on Pluto. It doesn't look like it's just a uniform ball, essentially. And if you zoom in on this and rotate it so that north is up, Pluto's got a funky coordinate system because it's tipped over in the plane of the ecliptic. And so, but if you rotate that so that north is up, and then you can compare it with geologic maps and things like that. I mean, geologic, there are place name maps at least since the New Horizons flyby. And here you can see, this is one of the 3 days we observed on 3 days. And you can see there are brightness enhancements. There are areas that are brighter than their surroundings. And if you look, again, geologically, where these areas are, there are 2 locations called Vega Terra and Periplanitia. And those are the ones that are brighter. And they're brighter by about 5 kelvins, which is significant. And for Periplanitia, at least, it looks like what's happening, and these are images from New Horizons, 2 of the instruments on New Horizons, Lori and what are called Lori and Ralph. And in the Ralph image on the right-hand side, purple is methane and blue is water. So it looks like what's happening in this particular area of Pluto is that the methane is sublimating. Sublimation is a process where something goes directly from solid to gas. There's no liquid state in between. And it's all due to the vapor pressure relation and what the temperature and pressure are at the surface. So the methane is sublimating and it's exposing the water bedrock below, and the water bedrock is warmer, just like on Charon. So it looks like this is what we're seeing, which is kind of cool. Okay, I'll have a bit of a fun aside. So the VLA is represented in popular culture regularly, representing science, technology. I mean, you'll see, I'll pick up a magazine and just see some random technology company that has a picture of the VLA antenna, and we don't restrict that. I mean, we're funded by the government, the National Science Foundation. Well, hopefully we're still funded by the government, and we're in what's called an FFRDC. NRAO is a federally funded research and development corporation. Same as Sandia is similar. I think Los Alamos is not. You are. Okay, so so it's not like we restrict access to these kinds of things. So again, I just see it all over the place. But some sort of popular appearances of VLA antennas in Carl Sagan's Cosmos, in movies, 2010, Contact, G.I. Joe, Terminator. And in music videos, Bon Jovi, Queensryche came out there. They actually asked for permission. Well, and Bon Jovi did too, I have to say. But Queensryche filmed a whole concert. They invited like 200 people, and they did a whole concert at the VLA site. And again, it's just I'll be watching TV and just say, hey, that's a VLA antenna. So this is Karl sitting in front of an antenna. Roy Scheider in 2010, This is CGI. They did not actually come and blow up our antennas and then contact. They did actually come for a full week. I was the science advisor for Contact, so if you have questions about Contact, I was a postdoc then, so I could take essentially a month and a half off of work. And I worked with them for the week and a bit that they were at the VLA site, and then I flew out to Hollywood while they filmed on the set, which was pretty spectacular. So yeah, that was a pretty amazing experience. So that's all I have. I'm open for. Yeah, Lisa's very happy because I finished early. I told her last night, nobody's ever unhappy when you finish a talk early. So if you have questions, I'm here. We have some time. So thank you.
Testing. Yep. What's the status of the enhanced VLA, and what will it do for planet observations?
Okay, so the enhanced, the EVLA, we finished that upgrade project. The next big thing is a thing we call the NG VLA, the next generation VLA. So we got some money from the NSF to build a prototype antenna, which is actually just completed out at the VLA site. It's a smaller antenna, 18 meters, different kind of configuration than the VLA antennas. And we've had almost 10 years of sort of a dribble of design and development money from the NSF, but that's at risk now, of course. So we're working with the NSF to try to get some more secure funding for the NGVLA. It's got a lot of community support, even internationally, and it's not new technology. It's all sort of proven technology, so we're not cutting edge. So we're hoping that goes through. And at one point, we were going to start construction in 2028, but that's clearly optimistic. So, you know, if we start construction in the mid-2030s, that might be more realistic. So.
Oh no, I'm happy to jump up here.
Hi, Brett Skinner, University of New Mexico. Thank you for the wonderful talk. I was curious on the brightness temperature slide of Pluto. At the longest wavelengths, the error of those instruments and studies skyrocketed. Is there a particular reason at those wavelengths it was not as sensitive?
Yeah, they were typically done with small single dish telescopes. So, I mean, small, 10 meters or so. The Caltech Submillimeter Observatory, CSO, and the James Clerk Maxwell Telescope, JCMT. So they were just smaller, less aperture, less photons, so less sensitive. And as you get into as you go to these longer wavelengths, the emission goes like 1 over lambda squared. And so you have less emission and a smaller telescope, and so it's just a byproduct of that. And if you put the ALMA data points on this, they have very tiny error bars.
Would you talk a little bit about, like, if a researcher is granted time with the VLA, I mean, how much time do they get? Is it hours, days, weeks? And then how do they get the information? Are they sitting back at their university? How does that work?
Sure. They get as much time as they need. So you have to justify it. So you write a proposal and you say, here's what I expect to see, the emission level that I expect to see. And then we have what we call an exposure calculator that says, here's how long you need to observe to reach that level. And they have to justify it, why they need that. And if they do that, and scientifically it's deemed important enough, then they are given time. we've had projects that are thousands of hours, individual projects. Typically, a project is more like 10 hours, a single project. And what happens is the observing happens quasi-automatically at the VLA. It's dynamically scheduled, so you don't know when it's going to happen. It used to be, so when I was a student and up until about the mid-2000s, that there was a fixed schedule, and you actually kind of needed to go to actually all the way out to the site. We stayed out at the site in what were called the visiting scientist quarters, because the data, which is tiny by modern standards, but it was too much for computers at most institutions. So the NRAO had powerful sort of mini mainframe convex supercomputers that we used to process all the data there. Now, there was an interim period where you could just download the data. We have an online archive. We always have, for almost 30 years, and you can just download the data and process it on your. I could process it on my laptop for many years. Then when we did the enhanced VLA, the data volume went up by almost 2 orders of magnitude, and so we reached a point again where most people at their home institutions don't have the capability to reduce the data. So we provide a post-processing cluster and a data reduction pipeline that they can sign up for. They can sign up for hours on, and we have staff who help them do their data reduction. So what comes out in the end is an image, essentially, but what goes in is actually what are called visibilities. It's a radio interferometer. Well, any interferometer doesn't directly measure an image of the sky. It measures a Fourier transform of that, and so you have to take that and do what's called deconvolution, which is an inverse Fourier transform to get the image. And so we have software to do that. There are other softwares that do that, but we've been developing ours for a very long time, and so they sign up for time on our cluster, and they use that to get their images.
Hi, I'm Jason Hick, layperson, fellow computer scientist. Bear with me. So you have a lot of, I think early in the talk you talked about vertical measurements that you're able to do. I'm curious, maybe in lay terms, like kilometers, or maybe from outer atmosphere all the way down to what might be interpreted as a surface. Are you able to do measurements all up and down, or like how deep are you able to go?
So typically on the giant planets, well, you can convert to kilometers, but we think in terms of pressure. That's the important vertical quantity. We don't measure to the surface. The cores of the giant planets are very, very deep down, and in fact, we don't even really know what they are. We think we have ideas, but like in the core of Jupiter, Jupiter is massive enough that it's probably metallic hydrogen, or at least a sheath of metallic hydrogen over something, but we don't measure near that deep. So we're really in the sort of upper skin of the atmospheres of the giant planets. But again, we measure. It depends on the wavelength, but at our longest wavelengths, we measure down to tens of bars, so sort of 10 to 100 times the pressure of the surface of the Earth.
Okay. And then how long do some of these reads take for the graphs you've shown? Are these representative in hours, days, months to get the data that you have?
Typically hours.
We have lots of New Mexico students here, and we have these fascinating laboratories and research facilities. And I was wondering, which kind of advice would you give them to all these folks who are here, who are admiring what we do here in New Mexico, and see you here standing up and telling us that you were a postdoc at the BLA and so on. So what kind of advice? Oh, you already did it. I missed that part.
Yeah. So, yeah, for those that missed the first, fourth grade me is saying, I want to do science fiction, and then you get more serious and you do all this school, but you end up with a career that hopefully you're happy with. So I would say the most important thing is follow your path.
Okay. Thank you. And I think that is it for that. Okay. I have to ask you about the thing. I think I can stand over here. There we go. Let's welcome our next speaker, please. This Matt Heavner is going to talk to us about this planet, as John reminded us in case we forgot that we are on a planet. So Matt's going to talk about that planet. And as he's
Okay. Okay, back. Thank you. Good for everybody that we're back. And then, so what is a planet? How do we study planets? And how does Earth, thinking about Earth, inform that? Okay. So one of the things Bryan talked about in terms of being inspired is fiction. Most of my talk is not fiction, but The Hitchhiker's Guide to the Galaxy, if you haven't read that, that's required reading for my class. And it's got good advice. Don't panic. As we're thinking about things, the environment we're in, government-wise, don't panic too much. But I wanted to talk through what is a planet. So the word planet comes from Greek, and that meant wanderer. So put yourself back in ancient Greek times. We're sitting here on the Earth, and we're looking at the fixed stars, right? We think they're fixed, and we see a few things wandering around. So what were planets? What were the wanderers? Earth, Moon was a planet. The Sun was a planet. Mercury, Venus, Mars, Jupiter, and Saturn. Those were the planets. Oops, not Earth. Earth's not a planet. We're not they didn't have that perspective. So we'll evolve a little bit. Copernicus, 1400s, 1500, he had this model that the sun's the center, not the Earth. So that changes our perspective. That's what we're trying to do. Actually, Aristarchus of Samos, to give credit, he came up with this sun-centered perspective. Yeah, come on in, join us. We're going to start moving in just a little bit. So in the 3rd century BCE, Aristarchus said, oh, the sun's the center. So if the sun's center, who are the wanderers? What are we thinking about? Things going around the sun are planets now. So Earth gets to be a planet now. Good. The moon's not. Sorry, moon. But then we discover other things. For Lisa, Uranus in 1781, Neptune came along. But then we found other things like Ceres, asteroids. All of these things started coming along that we discovered that were going around the sun. So we'll make those asteroids. Those are minor planets. Those aren't real planets. Then Pluto comes along, 1930. I'm glad you included Pluto in your talk too, because I'm going to hit on that a couple of times. Pluto is a planet, just in case there's any questions. Eris, Hamual, it's a planet. And I've got my next slide is on that. Maki Maki. All these things started popping up. Okay, so then the IAU came in, resolution in 2006, and said a planet in the context of the solar system, so we're not thinking exoplanets, but a planet orbits the sun, orbits a star, it's spherically shaped, it's cleared its orbit of similar-sized objects, and it's not a satellite. That's the definition of a planet. They said Pluto's not a planet. Now, rogue planets are cool. I don't know if we're going to talk much about rogue planets. They violate the first one. They don't orbit a star, right? So rogue planets are cool, but that's a whole nother talk. I forgot to ask at the beginning. I know we've got folks from outside of New Mexico. Who's from outside of New Mexico? Okay, not as many as I thought there might be, but before I go into that, let's take a pause. I need to catch my breath. Make sure we're all good. Right after sunset, we can all think deep planetary thoughts. So we've established a little rapport. Now I'm going to try to change the way you think. This is a real challenge for Saturday morning. Here's where we start playing. Is this the Earth? Raise your hand if you think it's the Earth. Is it not the Earth? Raise your hand if you think it's not the Earth. Is it both? Both. This is from Mars. Looking at Earth. Yeah, it's both. I got everybody almost. Okay, we're going to keep playing this game. So, yeah, this was Curiosity rover right after Martian sunset, looking back to the Earth. So this is Earth as a planet. We think of the Mars is what we're used to. So we're going to try to think a little radically here. We've established and agreed Earth is a planet. And Pluto is a planet. So in 2007, New Mexico passed the House Joint Memorial. As Pluto passes overhead through New Mexico's excellent night skies, it is declared to be a planet. No question. Exoplanet, minor planet. And so this is not a real photo of Pluto, but it is a NASA composition. And I like it. They wanted to put it over the US, but they put it over New Mexico. So NASA proved that Pluto is a planet. All right. What are the attributes of a planet? And Bryan hit on some of these. I'll go through a bit of these very quickly. So we're going for breadth, not depth. What is it made of? Is it ice cream? Is it cheese? Probably not. Is it geology? Most likely. What's it made of? How big is it? Is it roundish? What's the shape? Have there been big impacts that cause big craters? What does it look like? What's the mass? How dense is it? Is it gas? Is it solid? What's the orbit look like? Is it tilted? How's it rotating? Is it spinning? Is it gravitationally tidally locked? Does it have a magnetic field? Are there natural satellites? Are there rings? We heard some of the discussion on some of the rings of different planets. What is the energy balance? And I'm going to talk, I think I've got one slide on the energy balance. Does it have an atmosphere? Is it warm? Do we need to pack our long johns if we go visit? Or sunscreen? Probably both, but oh, I gave it away. We're going to try again, and I'm going to get more coffee. So, Earth. Anybody think that's Earth? Not Earth? You guys are catching both. You're catching on. So this is a picture from Mars looking at Earth and a moon. Not the moon. That's Phobos. That's one of Mars's moons with the Earth. So that's both. That's what Earth as a planet looks like. I could spend the rest of this lecture on going through these details. I'm not going to. You can thank me later or not. But I talked about the different parameters we want to consider. You can see how many moons are there? Are there rings, magnetic fields? What's the density? So comparing the Earth to other planets is a good way to do this comparative planetology and think more about the Earth as a planet. There were a couple of things. This was updated from NASA within the last month, and I was very happy to see they include Pluto. I don't know if they include the moon too. I mean, it's good to compare. We've got a couple of talks on the moon later, so it's good to have that comparison frame. I'll point one thing out that's interesting. After you've spent your entire PhD studying planets, then you can go into this and know every little detail. But if we look at the Earth's gravity, we all measured that this morning, right? We look at the density of different planets. I'm going to poke right here. So these, the moon's an anomaly. Mars is a little less dense. But these are all 3,000 to 5,000 kilograms per cubic meter. And these gas giants, or the gas planets, are less dense. Anybody know water this morning? Water's 1,000 kilograms per cubic meter. So Saturn would float. If we had a bathtub big enough, Saturn would float. So looking through these tables is kind of cool. I'm focused on the moon. I'm sorry. I'm focused on more coffee after this talk. I'm focused on the Earth. And so I'm going to be a physicist. Everything is one. That makes the math so much easier. That's the trick, right? But you can compare everything else. We'll get off this boring table. One slide on subsurface. We've got to talk later on today about more of this. But how do we know what the Earth is made of, or any planets, right? So we've got these models. I'm going to talk about seismology just for a second. That's a great way to figure out what's inside the planet. We can't look inside the planet. We can't take radio waves inside the planet. So we can look at some impulsive event that creates a sound wave that goes through the planet, and we can measure that, and we can look for how does it propagate, what's the speed of it look like, and we can figure out what the geology is. And so this seismometer is from the Earth. It's actually from about a mile that way. It's down in our garage, and this is from yesterday. So I'm trying to measure what the Earth is made of just to make sure it hasn't changed overnight. But this cartoon here talks about a lot of the processes that are going on, and I wanted to talk just very briefly about one of the first big science projects that I was involved with, MAMBO. Key is coming up with good names. MAMBO was the melt at the Mohorovic boundary. And what we did, we took about 30 ocean bottom seismographs, or seismometers, and put them about 3 miles under the ocean, right along the East Pacific Rise, so about 300 miles off the coast of Mexico. And we didn't want to wait around for earthquakes to happen, so we had an air gun. So we spent 3 weeks going around on a boat, firing this air gun, looking at the seismic signals through the water, through the different parts of the subsurface, and measuring specifically what is this melt. Can we get better information and understanding about the melt? Because at each one of these layers, the density changes, and so the speed of sound changes. And so if you have an array and you know where the source is, you can do ray tracing and you can get information. You basically do an inversion and figure out what the subsurface looks like. So we've got the seismometers, and we can put those on other planets. How many planets do we have seismometers on? I think it's just 2. I'm not sure. Just 2? Yeah, Mars. The moon has a lot of seismometers. The Apollo missions put seismometers up. But that's how we can learn and understand the subsurface. All right, we're going to work our way up. That's all you get, Lisa. Sorry on geology. We're going to do some more visual and some more movement. Earth? Not Earth. Okay. Both? Not Earth. Yeah. Mars. Yep. And you can see I added the credit for each one, but I took that off on the first chance you get to look at it. So this is from 2021 Perseverance rover. We'll hear more about that later. Earth? Not Earth? Both? Bisti Nazin Badlands, about 100 kilometers that way. I'm working on my spaceship, but I took this picture in 2021. If you haven't been out here, I recommend it. And this is, I don't want to just play this game and have fun, but you can look at various structures that you get just from images, and you can say, oh, that looks like there's some water on this planet. That might be good for making coffee in the morning. I like this planet. But you go back to Mars. Oops. Is there evidence of water here? I'll leave that for the next speaker. All right, one more. Well, lots more, but Earth? Not Earth? See the trees up there? Yeah, there's a little tree action. But sand dunes, there's some snow. There is a little water sitting around here. So we get similar things on Mars. Not so much water just hanging around. So, yep, this is my spaceship, but still in progress. This is the Kobuk Sand Dunes up in northwestern Alaska, north of the Brooks Range. So this is like 3,000 kilometers that way. Okay, Earth. Couple Earths, not Earth. Yeah, people are okay. Yeah, Mars, but sand dunes, some water. So just looking at the geology, looking at the surface is really instructive. So NASA JPL 2008 from HiRISE camera. Earth. But what's different from all the other pictures that I've shown you? It's ocean. We're not actually on a rocky planet. We're on a water planet. And we don't think about that. That's sort of our bias. We walk around, we go hiking, we take all these great pictures. We're like, yeah, we know what the Earth is as a planet. This is what the Earth is as a planet. So last night, I don't think she's here today, is she, John? But we had the deputy program manager for the Discover mission. And so I wanted to shout out, this is a last week image. And the concept for this satellite was we have a satellite sitting at L1 that looks down and does real-time like TV video. You can always look at the Earth as a planet. This is the planetary perspective. It's not quite that frequent. I think it's a couple dozen images a day, but you can go and you can look at the full disk image of the Earth. So this is Google Earth cleaning it up just a little bit. So this is a montage of a lot, but you got Baja over here. There's a little bit of Alaska up here. Australia's over here, but it's a water planet. 70% is water. So I sort of led you this way, but our bias was Earth is a rocky planet, and it's not. It's a water planet. Earth, Titan. Okay, so you gave it away. We got to get the right. Titan, for sure. But water features. So just looking at the surface, we can gain a lot of insight. So, yep, Huygens probe going down into Titan. Earth, not Earth. Most people go with Earth, yeah. Or both? No, it's... Yep, there's water up there. So this is off the coast of Alaska from my spaceship. No, it's an airplane. It's as close as I get to a spaceship. But yeah. So we talked a little bit about, is it rocky? Is it ocean? Is it frozen? What's the temperature? So just flying through and thinking about Earth as a planet. I talked a little bit, I teased that I was going to talk about the energy balance in one slide. So this is a reference to the atmosphere of the Earth. What we want to understand is how much energy is coming into the system. Is the system generating its own energy? Jupiter generates a lot of its own energy. How is the energy bouncing around in the atmosphere? How's it interacting? What are the different wavelengths that are involved? What are the processes? Are there phase changes? So latent heat is phase changes. We talked about different types of phase changes, water to ice, cloud formation. And so I'm not going to go into detail on this, but understanding the energy balance and the energy flux around a planet is a key part, especially as we try to understand what the atmosphere of the planet looks like. All right, this one's a challenge. Earth? Not Earth? Not sure? Earth. This is Earth in infrared. So the first talk was about radio waves, but had a lot of optical. But we need to think about how we see things. We're biased by how we see things. We go out with our camera and take lots of pictures, and we think we see what's there. But this is a picture of the Earth in the infrared. And so different wavelengths look incredibly different. So we want to make sure we're not biased by how we're viewing something. This one is the Earth. I won't make you guess, but this is in the extreme ultraviolet. So this is the image instrument. And this is looking from the north pole of the Earth down in the ultraviolet. So the sun is off in this direction. There's a shadow here. You can see the aurora, but Earth looks totally different in the extreme ultraviolet. So I want to take a quick moment to say how we're looking at something really determines what we see. It's kind of obvious, but don't get fooled by your assumptions of my eyes work at a certain wavelength. I know what the Earth is. All right. We're going to talk about the atmosphere just a little bit. All right. This is from the ISS. This is the Earth. This plot is from NASA. And there's a couple of different aspects around the atmosphere that I just wanted to quickly cover. There's different layers, and those have to do with the temperature in the neutral atmosphere. So these are neutral gases. This is the oxygen we like to breathe. And there's different processes in each of these different parts of the atmosphere. The scale here is 0 kilometers up to 400 kilometers. So here's the Kármán line right here. ISS. Oh, perfect. Thank you. I like these lasers. They're fun. There's a lot of processes that go on. The aurora, I'm going to talk about that just a tiny bit. There's different ways we measure aspects of the atmosphere. Sounding rockets flying through. Bryan talked about doing that up in Fairbanks. LIDARs, lasers, cool, going up into the atmosphere. Radar, the RF, the radio frequency work that Bryan was talking about. Optical imaging of the aurora, sending balloons. So this is all neutral atmosphere. There's also the important part of electron densities. You can see the electron density is very low here, but as we go up, there's more electrons. What's happening is there's more energy, more energy from the sun coming and stripping electrons off of the molecules in the atmosphere, ionizing them, or even disassociating them, taking the oxygen we like is O2, molecular oxygen. The sun can shoot a photon and split that, and so we have atomic and ionized atoms. What that means is electric and magnetic fields become a lot more important, and we get into plasma physics. And that's cool because that's what the aurora is all about. One of the key things I had, one of the key parameters thinking about planets is there a magnetic field? What does that mean? What are the processes? What are the things we'd observe related to the magnetic field? I want to catch my breath and tell you one more project that I'm involved in. And this is a great one. This is hosted by the NMC. This is Aurorasaurus, which is a citizen science project trying to get people to report their observations of the aurora. So if you see the aurora, you should report it through aurorasaurus.org. One of the things we did with this Aurorasaurus was hold a winter field school this January up in Fairbanks, and we did classes and lectures through the day, and then we'd go out and chase the aurora successfully. I forgot to do the game Earth. Yes, okay. Yeah, we didn't get off the Earth for this one. But this is the group photo from the first night. And so we've got a lot of work on the aurora going on and thinking about what does that teach us about Earth, and then thinking about Earth and understanding the aurora and the space weather. How do we then translate that to more understanding about other planets? All right, Earth. Not Earth? You guys aren't playing along. Come on. Earth. Okay, not Earth. Jupiter. There's aurora everywhere. Everywhere. If you've got a magnetic field, even if you have a really weak one, there's some aurora. And that's a whole nother lecture, but thanks for playing along with my game. So, yeah, this is actually, I meant to thank you, John. We would not have this because this is from Hubble. And so John will give the talk at the end of the day. But it's he put the contact lenses on Hubble that let us get all the Hubble data. So thank you, John. We wouldn't have this photo of aurora from Jupiter without that. All right. Aurora is a lot of magnetic phenomenon, but it's electromagnetism and it's plasma. So I want to talk about the electric field just briefly. So if we think of an electric circuit and we think of the Earth, I'm going to simplify it and think from a not an alternating current perspective, from a direct current perspective, just your laser pointer with batteries and a bulb. You need something to charge up a system, you need some conductors, and then you need something to discharge it. And so if we think of the Earth and the ionosphere is roughly 100 kilometers up. Those are the two plates in a spherical capacitor. And there's electrical phenomenons. There's basically a battery and a spark between those two plates. And so what's charging it up are thunderstorms. They're occurring on about 1% of the Earth's surface. And then there's a leaky electric field that's discharging the Earth electric system. So this is just another perspective of how we think about the Earth as a planet, as just a simple capacitor circuit. And then we can apply it to other planets. Looking at this for Jupiter and other planets is great. Earth, not Earth? What the heck is this? This was the subject of my thesis, so I could talk forever about it. This is sprites, and this is Earth. It is a NASA astronomy picture of the day. But basically, let me go back to CTR Wilson's rough sketch. We've got lightning that we know about going from clouds down. What's going on right here? So there's a lot of electrical activity that's going on up above the thunderstorms that connect. So the thunderstorms are typically about 20 kilometers, and we said the ionosphere is about 100 kilometers. So we're used to watching all this great lightning down here. But there's lightning that goes up and connects to the ionosphere. And that's what these sprites and jets are all about. So I could talk for an hour about just this picture. Do I have that time? No, okay. Here's a slide from my thesis, so I could really talk about this one. But this is back, we talked about the temperature profile of the neutral atmosphere and the electron density. So we see this ledge right here is the onset of the ionosphere, right about 100 kilometers. I talked about the storm charging. We've got different kinds of lightning going on in the storm, lightning going to ground, positive, all this lightning that I could talk about forever. We've got these sprites that complete the circuit going up. So not just thinking about the aurora, but thinking about electrical phenomenon that's going in the atmosphere. And then that feeds into what chemical processes is this driving? How does this interact with our ozone layer? There's tons of interesting atmospheric science going on here. I think one of our charges was also talked about the great work that goes on at the lab. So this was the project that brought me to Los Alamos back in 2000. The FORTE, the Fast On-Orbit Recording of Transient Events, back to good acronyms. But this was looking for radio impulses, so great big antenna looking at, this is the Earth, okay? But by looking at lightning as a source and making radio measurements from space and from the ground, we could triangulate, we could measure the height of the ionosphere, we could look at atmospheric electrical propagation. I'll talk just a second about these field change meters. Who has ever seen an AM radio in a car? If you're cruising around with your AM radio and you turn it off of the music and there's a thunderstorm, you hear these pops. That's the RF emissions from lightning. And that's basically what these are measuring. So if you have 2 or 3 of your friends driving around with their AM radios and you say, yeah, I got that one, you can figure out where it occurred, you can geolocate it, then you can figure out how high in the atmosphere it's occurring. So looking at, our earlier talk was all about radio frequency observations, try to understand planets. So similar radio observations of lightning on Jupiter have gone on. But this method really helps us understand more about Earth, electrical processes and Earth as a planet. So I'm wrapping up. 3 minutes, yes. Earth. I want to talk about rings and moons just for a second. Earth, yeah, we got one. You're a small step ahead of not Earth. Both. So, no, that's there it is, right there, and the moon. So this is Cassini on the other side of Saturn. Looking back, it's a little distorted because it is eclipsing the sun, but the surface is still so bright they had to do a lot of image processing, so you get the beautiful rings. Bonus, Venus and Mars are also there. So rings, moons, that's a whole nother aspect. And I just wanted to tease you with this. Oh, there we are again. That's Earth as a planet. Most other planets, that's how we see them. That's how they see us. Talking about rings and moons, we're creating a really cool, we're going to have a nice iron ring. And this is pretty close. So this is all the LEO, and this is from 2021. So this is pre-7,000 SpaceX Starlink satellites. So it's only better or worse. I won't make a judgment, but it's more crowded up there. But you can see this line of satellites. There's the geo belt, geosynchronous. So this is probably 200 kilometers up to maybe 1,000 kilometers is where this is. Geosync is 22,000. So it's way off the screen, but it loops right through here. It goes all the way around. So we got a big ring of geosynchronous satellites. So we do have a ring, not a natural ring. To wrap up, oh yeah, okay, Lisa. Earth, not Earth. Yeah, this is Carl Sagan's pale blue dot. That's the Earth. I want to sum up with Hitchhiker's Guide to the Galaxy. I think this is a good perspective. Hopefully we are wrong to think that we could now forget that this big, hard, oily, dirty, rainbow-hung Earth on which we live was just a microscopic dot on a microscopic dot lost in an unimaginable infinity of the universe. So that's how I want to sum up thinking about Earth as a planet. Or it's mostly harmless. If you've read The Hitchhiker's Guide. So my references, this book is actually out at the book sale. This is a really fun one. So this is The Lonely Planet. Tried to do a travel guide to the universe. And it's really fun. I recommend that. I love reading through that. When I taught planetary science, this is the book I used. This is, I don't know, Bryan, is this the Bible for planetary science? I think it is. But this is a great source. And then don't panic. Perfect. And I've got extra time. I should have gone longer. There's yours, Lisa. There's your bonus slide. Ooh. You don't just need photons. Things can come visit.
They do come visit. Awesome. I didn't even have to get up and sideways crab rock. I knew you were finishing.
I was looking forward to it, but
it's still there. Questions from the audience, please.
Hi, thank you so much. I wanted to ask about the research project that you worked on. I'm wondering, maybe I missed this, is there a correlation between the lightning strikes that we get that appear to us and you said the sprites in the ionosphere? And if so, does one cause the other? Or are they both caused by some other third thing?
That's a great question. Thanks. Read my thesis. No. The shorter answer is, I think I'll actually go, I will use this one. So because of the energy balance in the atmosphere, that drives convective processes, and that convection actually creates friction, and that creates phase. It creates energy and charge separation in the thunderstorms. And so as the storms grow, there's more charge separation, so there's a small capacitor inside the cloud, and that starts discharging. 100 to 1 are discharges down to ground, cloud to ground lightning. That's negative. And so it has to do with the polarity of how the discharge works. There's a lot of details there. But occasionally you get positive cloud to ground. That's about 1% of the cloud to ground lightning. These positive cloud to ground lightning are generally higher current. And so if you get a discharge, then you drive fields that go up into the atmosphere. So each discharge creates an electric field. And that electric field creates an imbalance in the middle atmosphere. So you get charge separation, you get fields building up in the middle atmosphere. As this storm develops, occasionally, instead of the charge going to ground, you'll get a big discharge, and usually it's a cloud to ground goes, and then that big instantaneous field change triggers the discharge here. These discharges are neat. They actually start right about 70 kilometers, and they propagate down and up. If you have a high-speed camera, you can see it propagate, and that's when you get. That's cool. You get these beads that go, and then you get these tails. It's really fancy. I mean, you can Google high-speed images of sprites and watch. They're really mesmerizing.
Matt, what's the scale bar on that?
This is probably about 30 kilometers, and this is about 100 kilometers. This is 70 kilometers, and each one of these are about, well, this is a fun fact. So, fun fact. A typical cloud-to-ground lightning flash is about 10 centimeters big. You know how you measure that? You put out chicken wire and you launch a model rocket with a copper wire, and you'll see how much burns. Truly, that's how you do it. Oh my God, you can't have a chicken wire up here, so you use a couple of cameras. You triangulate, and these beads and balls, these are more tens of meters kind of size. And this is, so this is 50 kilometers. So the scale is much bigger because the density is much lower. So down here, part of that, we need bigger fields and we have really small discharges. So more info than you asked for, but now you know
That
what to do
was-
with your chicken wire.
I always wondered. I was just sitting in the yard.
Yeah.
Other questions? I have a follow up since you have this slide up. Is the sprite phenomenon has that been observed on other planets?
Sort of.
Nice.
Yeah, good answer. Jupiter's lightning is more typical of this kind of sprite because of where it occurs and there's no surface. And so it's in Jupiter, it's all atmosphere, kind of. And so the densities are different, the field strengths are different, but it's generally much larger lightning in Jupiter. And so I think Jovian lightning has this sprite-like activity, but we haven't gotten any pictures of sprites on other planets yet.
Just Jupiter, maybe.
Well, there's a billion planets out
Well-
there, right?
Right. We'll get to exoplanets then. Pause for another question. If not, yes. Colin's got it.
So I was curious if you could go back to the slide of the ultraviolet on Earth.
The EUV or the IR? Let's see.
The one where you can see the aurora, that one.
Yes,
So
extreme ultraviolet.
Is that plasma pause? Is that just the like solar wind and like the ions from the solar wind getting trapped in the magnetic sphere, or is that some that's escaping and hitting the atmosphere of Earth?
Good question. You had the right sense of it. That's where the solar wind and the Earth's magnetic field boundary is. And so that the plasma pause is where the solar wind is getting more deflected around the Earth's magnetic field. So that's sort of the edge of the Earth's magnetic field as the solar wind is pushing against it. And on this case, since the sun's here, the sun's pushing in this direction. And so that's the back edge of the Earth's magnetic field.
And then I have another follow-up question with that. So because we have that capacitor system, could
Right.
the positive ions and the negative ions in that plasma that's getting trapped lead to the sprites actually being a reason they form?
Let's see. I think I know what you're asking. So because we got the capacitor system and we've got ions building up, is that where what causes the sprites? Yes. Do you want more detail?
Nice.
So
yeah.
the challenge is the atmospheric scale height is about 7 kilometers. And so every 7 kilometers we go, there's an exponential fall off. About 70% of the atmosphere is gone, so it's less dense. And the density really changes the chemistry of how quickly ions recombine. And so there's 10 scale heights basically here. And so all the chemistry processes are totally different along this whole 100 kilometers. And so the recombination rate is changing. And so here we live in a neutral atmosphere. There's not a lot of ions hanging around because they're all recombining. Up high, they're not recombining. And so there's ions and yes, all of that plays into where sprites form.
Okay. Thank you so much, Matt. That was very cool. Thank you also to Bryan. We have a 20-minute break now, so we reconvene at perfect timing at 10:40 for our remaining 2 presentations for the morning, and then we have an open panel Q&A with our speakers. So see you soon. That's a great question. I was like, holy shit. I'm just like, talk about planet more, please.
More
geology. Yeah. You know what was great? You know, that was beautiful. It was not what I expected, but you know what? I didn't know because I realized throughout this talk, I was like, oh, that's what Matt did for his thesis. I don't know how I didn't ask. Anyway, hi, Dave.
I'm now curious about what, 'cause I've got a Mac also with the USB.
I brought this if you need
Well,
it.
I have a bunch of adapters, but so
Test
they
it
were
out
just
and
saying,
see.
yeah, I'll do that tomorrow morning early.
In none of your slides do you mention the asteroid belt in the context of